Now we're going to take a look at some division problems. So how would you divide rational expressions? The first step is you're actually going to take the rational expression that is on the right. So here that would be 2/3. And we will flip this and multiply. So we're going to change every division problem into a multiplication problem. So then after that, we're just doing the same steps that we learned from the last video. So if we have this as 1/2, change this division problem into a multiplication problem, and then flip this upside down. And then just like we would do multiplication like we practiced in the last video, we're combining these two fractions together. So I have 1 times 3 all over 2 times 2, and that gives me 3/4. All right, so that's a pretty simple example. Let's try it with something that you're probably more likely going to see. So here we have to factor a little bit and do some work to find restrictions. So here, I'm always going to focus on the rational expression that's on the right. Okay, so don't flip the one that's on the left, or you're going to end up getting the wrong answer. So you have to flip the one that's on the right. So we'll start off by doing that. So we get x squared plus 3x minus 40 all over x squared plus 2x minus 35. And now this division problem changes into a multiplication problem. This gets flipped upside down, so I have x squared plus 3x minus 18 all over x squared plus 2x minus 48. Awesome. So now that this is a multiplication problem, I'm going to then factor everything. So all of these are just simple ABCs. They're just going to factor into two binomials. All right, so for the first simple ABC, for the first thing I'm factoring, I need two numbers that multiply to make 40 and they add to make +3, so that would be 8 and 5, where the 8 would have to be positive, the 5 would have to be negative in order for them to add to make +3. All right, next one, I'm going to have to use the numbers 5 and 7 to multiply to make 35, and 7 is going to have to be positive, 5 is going to have to be negative. Okay, next one, I'll be using the numbers 3 and 6 to multiply to make -18. 6 is positive, 3 is negative. And then for the very last one, I know that 6 multiplied by 8 gives me 48, and 8 is positive, 6 is negative. So the only different part about division is when you're finding the restrictions. Okay, so this is the big one where everything's going to change a little bit. Typically, right, like when we have this multiplication problem, we would merge these together and we would just focus in on the denominator. So that's not going to change. Like, we'll still look at all of the factors here and see what we're not allowed to plug in to the denominator, because we don't want the denominator to become 0. So we can't plug in the number 5, we can't plug in 7 or 6 or -8. But there's also there's actually 2 more numbers that we cannot plug in to this rational expression, okay? And the reason is, remember when we flip this, okay? So at one point, x squared plus 3x minus 18, this was in the denominator, okay? And we flipped it so that it wasn't. But if at any point in the problem something is in the denominator, you're going to include that in your restrictions, okay? So I am going to include this part right here, so the x minus 3 and x plus 6, because that's what this factored into. And I want to include those as part of my restriction. So I'm looking at both of those factors. And that means that I'm going to include +3 and -6, all as numbers that I'm not allowed to plug in, okay? So if at any point something is in the denominator, then we have to include it in our restrictions, okay? So we're getting restrictions from all of these factors except this one, because this stayed in the numerator the entire time. We don't have to worry about it, okay? Let's try one more example, so something a little bit more crazy. But if we were looking at something like this, this is just another way to format a division problem, okay? So I have like this first rational expression. So that would be equivalent to like this rational expression here. And then the second rational expression, instead of putting it off to the right side, they put it right underneath. So it's being divided by this. Okay, so that would be equivalent to this over here. So it's just another way to format a division problem. So I am going to now take the rational expression on the bottom, and that is the one that I am going to flip. Okay, so I'll flip this and then change it into a multiplication problem. So I'm going to rewrite this as m cubed plus n cubed all over mp minus mq plus np plus n cubed. Okay, and now I'm multiplying this by everything flipped upside down. So mp minus nq plus np plus nq. Okay, so for this one, I'm not going to worry about finding restrictions on the domain for this, just because there's a bunch of variables. So we're not going to worry about this for this specific problem. However, one thing I do want you to notice right away, though, is that there's these implied parentheses around these really big expressions here, where everything's being added, subtracted together. We assume that there's parentheses around these. And if you notice, these two are exactly the same. So when I merge these two fractions together, right, I can cross these out. Okay, so both of those are completely gone, and I'm only left with m cubed plus n cubed all over this. And actually, let's just jump into the step where we're factoring this a little bit more. So hopefully you were able to recognize that this m cubed plus n cubed, that is in the format of sum of cubes, right? So this is going to factor into a binomial multiplied by a trinomial, this part right here. So that's all that's left up in the numerator. And then in the denominator, I actually can't not factor this any further. So I'm just going to leave this as m squared minus mn plus n squared. Okay. But however, this sum of cubes, when I take the cube root of both of these, I get m, positive m, and then positive n, and same sign for that first one. If I'm using that method of SOAP, same sign, opposite sign, and then always positive when I'm doing sum or difference of cubes. And then the next term that I have in the trinomial is m squared. The sign that comes after that is the opposite sign of what I started with, so that's a subtraction sign. And then now I'm multiplying these two together to make that middle term. So mn. Last sign is always positive. And then at the very end, I just have n squared. So now that we're here, there's another set of parentheses around this that are implied. So these two factors are exactly the same. I can cross both of those out. And then all I'm left with at the end is m plus n. And then that would be what this giant, disgusting looking problem simplifies to, is m plus n.